Okay, folks, we can get going. Hope people had a good break. So what I would like to do today, we're still going through content related to Lab 2, of course. And what I'd like to talk through today is the pseudocode that demonstrates how you will be implementing the collision physics of the balls bouncing through the Galton board. I want to talk through this just a little bit. Many lines of it sort of speak for themselves, but there's a couple of lines here that are a little bit obscure. And so I want to talk through where those lines come from. I'm looking in particular at like this intermediate term, -2 times normal x, blah, 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 blah. I want to speak to this a little bit. And in order to speak to that, I want to briefly remind you of some stuff that you have most certainly seen before, which is elastic collisions between balls. But it may have been a while, and so I want to revisit it. So before I get into that, though, let's take just a moment that I want to just walk through this to point out a couple of gotchas associated with this pseudocode. So let me just remind you that every time you go through your animation thread, and you'll be going through your animation thread 30 times a second, you're going to do the following. You're going to look at each ball, and for each ball, you'll look at every peg, and effectively what you're asking is this ball in collision with this peg? And in the event that those two are in collision, you do the physics to figure out how the ball moves as a consequence of that collision and update its position. So 30 times a second, you are going through, erasing every ball, recomputing the velocity of every ball, which may have changed because of a collision, and then recomputing the position and redrawing as a function of the velocity. A couple of things to just note here. So, by the way, this is the most naive, most unoptimized version of how one might do this. As you look at this right now, you may identify some opportunities to speed things up, and there are many. I want to give you that opportunity to do that optimization, so I'm offering you the most naive version of this. So for every ball, you're going to go through every peg. Note that what we are interested in learning is the difference in position, the distance that is, between the ball and the peg. The distance is computed here, distance equals square root of dx squared and dy squared. I just want to point out that before we compute the distance between our ball and some candidate peg, the first thing we do is compute the x and y differences in position between that ball and that peg, the dx between the ball and the peg, and the dy between the ball and the peg. And then we ask, is the difference in x position less than the sum of the radii of the ball and the peg? That is to say, is the x, am I close enough in the x direction? And same question for the y direction, am I close enough in the y direction? And only in the event that I detect that my x and y differences in position put me in a location where I may be in collision, do I then subsequently actually compute the distance, the root sum of squares? And there's two reasons for that. One is that root sum of squares is an expensive operation, naively implemented. You may be interested in going through the reading here and reading in particular about the alpha max plus beta min algorithm. Ooh, that's a sneaky way to speed up that step. We can talk about that a little bit later. But in any case, we don't want to do any arithmetic that we don't have to do because we're trying to get through this whole thing as quick as we can. And so in the event that we can just tell that we're not near that peg, no reason to go through the rest of this, right? We'll just jump to the next peg or the next ball or whatever. The other reason to do this is remember that in order to implement this animation as quickly as you can, you will be working in fixed point. You'll probably be working in 15.16 fixed point, which means the range of your fixed point values can be as big as like 2 to the 14th. Let's suppose that our ball and our peg are really far away from one another on opposite sides of the screen. And let's suppose that we didn't do these checks in the x and y separations before squaring dx and dy. What could happen? So let's say dx is 620 pixels. Let's say dy is 450 pixels. Square 640, that's a pretty darn big number. And in fact, it's so big that you're going to overflow your fixed point data type. And so this ball and this peg that are in fact on opposite sides of the screen, if you overflow it, that overflow is going to give you a really small number, and the ball is going to bounce off of nothing possibly, right? Because it thinks it's in collision with this peg. So that would be the symptom of an overflow error here would be ball bounces off of nothing or something like that. By the way, the most consequential overflow error that I am aware of. Has anybody heard of Ariane 5? I'll do just a 2-minute tangent. Ariane 5 was a rocket built by Ariane Space, I believe a French company. Ariane 5 was the successor to Ariane 4, a smaller rocket. It had 2 redundant flight computers. Those flight computers were running exactly the same code. They were both running, in fact, exactly the code that had run and worked beautifully on Ariane 4. And so they said, this code works great. Let's just put it onto Ariane 5. There was a line in that flight software that did an unprotected cast from floating point to a 16-bit integer. And the value that was being cast was the horizontal velocity of the rocket. Now, Ariane 4 was a smaller rocket, and its horizontal velocity didn't get that big relative to Ariane 5. And so that cast, it was perfectly okay. Well, it was not of consequence that that was unprotected because it never overflowed that 16-bit integer. Ariane 5 was a faster rocket. And when they did that type conversion, it overflowed the unsigned ints to which they were trying to cast. The flight computer was actually smart enough to recognize that's an error. And so flight computer A said, oh, I've got an error. Let me pop over to flight computer B. Flight computer B, of course, had the same error because it was running exactly the same software. So flight computer A rebooted, and it was programmed such that on reboot, it would print out some diagnostic information, as many of our programs often do. In flight, that diagnostic information was interpreted by the flight computer as the horizontal velocity of the rocket. The flight computer went, oh my God, I'm going the wrong way, and gimbaled the engines really hard, so the rocket turned in air and the aerodynamic forces blew it up. So this was a multi-million-dollar consequence to what was fundamentally an overflow error. It was an unprotected cast from float to a 16-bit integer. Just to remind you that the stakes here can be high. The stakes of our error, pretty low. You get an errant ball. The stakes in that case were tremendously, tremendously high. And heartbreakingly, that line of code was not even necessary. It was an artifact from the Ariane 4 flight code. It was required for the Ariane 4 flight code. They said, well, we don't really need it for the Ariane 5, but if we take it out, we have to go through the whole set of test procedures. We know this code works. Let's just keep in this redundant, this unnecessary piece of code. Ended up costing the rocket. Keep an eye out for overflow. In any case, that's why we do that check. In the event that we think we might be close enough that we're in collision, we do in fact compute the distance between ourselves and the ball as the root sum of squares of our x and y separations. We compute the unit vector, the normal x and normal y vectors, that points from the peg to the ball. So this is the vector that goes from the center of the peg to the center of the ball. We then compute this intermediate term that I'm going to speak to here in just a moment. In the event that we are colliding with the peg, the only other line here that I wanted to point you to as being slightly unusual is you will notice that we teleport the ball a little bit. If we've collided with a peg, we're going to do the collision physics, but we also just teleport the ball a little bit back in the direction that it came. The reason for this is to avoid a situation where the ball, of course, is moving at multiple pixels per frame. And so when it collides, it's unlikely to just be overlapping by, say, 1 pixel. It's probably going to slide over the peg a little bit. And you could end up in a situation where you bounce like this inside of the peg, right? And so in order to avoid that bug, we teleport it out. That's what's happening there. And then the only other thing I wanted to point out in connection with this pseudocode, because I think the rest of it largely speaks for itself, is we make a sound. We trigger the DMA channel to make a sound whenever a ball strikes a new peg. And so this is one extra piece of state to keep track of for each ball is, what was the last peg that I hit? So in the event that you hit a peg and you kind of bounce, 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 bounce along the peg, you don't make a sound every time you bounce. You make a sound every time you strike a new peg. The reason for this is just playing around with this. That gave them what felt like the most physical experience. Clunk, 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 that kind of thing. Let me see here. The other thing I wanted to mention is we are doing a little bit of a cheat here that I wanted to speak to. Where is it? Right here. These 2 lines. When a ball strikes a peg, it loses some energy. It happens physically too. You strike a peg, you lose some energy to heat and vibration and sound and so forth. To be truly physically correct, the places that that energy would go when a ball strikes a peg would include the things I just mentioned, the sound that it generates, some vibration, some heat, and also spin. We are not modeling the spin of the ball as it bounces through the Galton board. Seems a little bit out of scope for a 3-week lab, but would be perfectly in scope for a final project. And so, in fact, when a ball strikes a peg, the energy that it loses as a consequence of that strike is almost all in the normal direction. It loses energy along the line that connects the center of the peg to the center of the ball. And it loses very little energy in the parallel direction. We're removing energy in all directions. Now, the reason for this is in playing around with this, in the more sort of physically correct version of this, but absent spin, what I found was that the Galton board, if you only removed energy in the actual normal direction of the collision, is the balls would skip through the Galton board, which perhaps makes physical sense. The nearest physical analogy that I could offer is if you could imagine that the pegs themselves are made of perfectly frictionless ice, and the balls are made of perfectly frictionless ice, so they just kind of click, 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 click. And that's not exactly the effect that we were looking for. And so we could address that by, I think, by modeling the loss of energy associated with spin, associated with each collision. Like I said, that's a little bit out of scope, so we're cheating a little bit, and we're saying just whenever a ball strikes, we're going to suck some energy out from sort of all directions. Ends up with a nice illusion. And that's what we're going for here, is a physically correct looking illusion, not an actually perfectly precise physical simulation. It's a computer graphics project. In computer graphics, if it looks right, it is right. And this looks right, okay? But the line of this that I wanted to speak to a little bit was this one. And in order to speak to this, like I said, I need to remind you of some collision physics. Now, I gave some thought as to how exactly to do this because it occurs to me that you all have done elastic collisions between balls, I don't know, probably 2 or 3 times in your academic careers so far. When you first learn about conservation of momentum or conservation of energy, the canonical problem that people use to talk about that is usually elastic collisions between balls. And so I don't want to stand up here and bore you with stuff that you will have seen previously. And also, in the event that the algebra associated with that is a little bit rusty, I think the best way to brush up on that algebra isn't necessarily for me to stand here and walk through every step. I think the better way to go about that is for you to sit in a quiet corner by yourselves and go through that. And so to help facilitate that process, the reading here includes a page that walks through every step of the algebra associated with this. And so I'll invite you, if you'd like to brush up on that, I think that's the best way to brush up on it instead of me standing up here and going through every algebraic manipulation. And so I thought what we would try, this is challenging, is that I might be able to use this as an opportunity to speak to the differences that I have observed in the way that engineers approach problems like this and physicists approach problems like this, which means I have to play the role of a physicist, which is challenging because I'm not a physicist. I have an undergrad degree in physics, and that's about the extent to which I'm a physicist. But I've had the opportunity here at Cornell to be in the sort of a community of physics students, and I've interacted with a bunch of physics students. And of course, I've also had the opportunity to be an engineering student and interact with a bunch of engineering students. And I've noticed some differences in these two communities. And the two communities approach problems like this in different ways. And each community's way of approaching the problem has its own set of benefits, its own set of drawbacks. And so it seems to me that it might be kind of valuable to the best of my ability, try to illustrate how this other community of folks might approach a problem like this. By the way, there are some physicists in the room, to my knowledge, and so if you disagree with any of this, by all means, correct me. But before I get going, maybe I can speak in the abstract to some of the stuff that I feel like I've observed. And let me just say, these are my opinions, and I have colleagues that may certainly disagree with these observations. But to speak, first of all, perhaps to I think the benefits of the ways that engineers tend to approach this problems like this, is engineers seem to be more comfortable, engineering students seem to be more comfortable than physics students that with doing this kind of analysis in slightly unusual reference frames and slightly unusual coordinate systems. And the reason for that, I suspect, is that we're often doing these problems in the context of some engineering project. So say you're solving for the dynamics of a spacecraft. Well, there's sort of a natural coordinate system in which to do that, but then also your gyroscope and your accelerometer is slapped on there someplace, perhaps not aligned with the principal axes, right, and perhaps pointed in some strange direction. And so you end up in this slightly strange reference frame of the sensor, and engineering students seem kind of okay with that. And in part, as a consequence of that, when you're working in a slightly unusual frame of reference or coordinate system, the equations get big and they get nasty. And engineering students seem okay with that. They'll just plow right through. A physics student, when things start to get big and nasty, that's often a clue that something may have gone wrong. Because physics tends towards elegance, at least in the classes here. Of course, in nature, sometimes that's not always the case. I'm thinking in particular of that big standard model equation that is on the front of T-shirts of people at CERN, right? Big, nasty equation. But generally in physics classes, the solutions tend towards elegant ones, right? And so those, I think, are and the other, I think, benefit perhaps that I've seen of the engineering approach is the engineers tend to be, I think, a little bit more comfortable in vector analysis because all of our sensors tend to spit out measurements in X, Y, and Z and so forth, and we end up with vector equations. Physics classes tend to be a little bit more scalar, with some exceptions. E&M is all vectors, but tends to be a little bit more scalar. Now, on the other hand, the physicists, in my view, are very, very good at. The engineering students seem to have no problem just plowing through the math, right? The physicists, I think, are very gifted at pausing and thinking at every step of this and saying, okay, before I go through this math, can I make my life a little bit easier? Is there a more natural coordinate system that I could be working in? In other words, it seems to me that the physics students have really internalized that our choice of coordinate system and our choice of reference frames is truly arbitrary. It does not matter. To a greater extent, I think, than sometimes the engineers have appreciated this. And so the physicists are very good at looking at a problem and saying, okay, ultimately, I want the answer in this reference frame, but who cares for now? What's the most natural reference frame in which to solve this? What's the coordinate system that makes my life easiest? Let me solve the problem in that coordinate system, and then as a last step, I'll just pop over to that other one, right? There tends to be a little bit of a tendency among engineers to say, well, I care about that coordinate system, so I'm going to do the whole analysis in that coordinate system, which makes your life miserable. So in any case, I thought that we could use this as an opportunity to talk through some of these differences. So we're interested in figuring out what is the dynamics of a ball colliding with a peg. The other thing, the physicist thing to do, is you always start with the simplest conceivable version of the system that you're interested in and solve that first. The simplest conceivable version of the system that we're interested in is a ball colliding with a stationary ball. We've all seen this problem before. And I'll just remind you that the way that we solve a problem like this is, well, there are things that we know here. Our knowns include the masses of the balls. Our knowns include the initial velocity of our ball. And our unknowns are the final velocities of the two balls. And so we have two unknowns. And by conservation of momentum and conservation of energy, we get two equations. And so I'm going to skip the algebra because I don't think it is of tremendous value to go through it. Like I said, it's all on that webpage. But we have two unknowns. We have two equations. We can solve for the two unknowns. And when we do that, we end up with the following expressions for the final velocity of the little ball coming in and the final velocity of the ball going out. Now, the other thing that I'll just point out that physicists are quite good at is you arrive at a solution like this and you very quickly check the corner cases. You go to the limits immediately and ask, okay, if I take this to the limit, does it make sense? If I take this other thing to the limit, does it make sense? So one of the things that we can do is see if this matches some of our physical intuition, because we can actually apply it to problems like this. And we notice that, all right, if that mass is bigger than that mass, the final velocity of the little ball is negative. That makes sense. It bounces off the bigger mass, right? In the event that the two masses are equal, what does this reduce to? The final velocity of the incident mass is 0. The final velocity of the other mass is the initial velocity of the first one. It's a Newton's cradle. right? So we arrive at our solution, and then we immediately check the limits and say, okay, does this make sense in the limit? Indeed, it does. So that's the simplest version of this problem. And as we'll see as we go through this and add layers of complexity, we save ourselves a ton of work by starting with this. This was easy. There's just a little bit of algebra between those two equations and these two equations. But as you'll see, it saves us so much work to start with this. Okay, so what's the next version of this? Well, almost the same, except let's add one layer of complexity, which is rather than having the ball that we're hitting be stationary, it's going to have some initial velocity too. And the directions of the arrows here are just arbitrary, right? But just indicating that both of these are initially moving, they collide, and then they're both moving afterwards. So it's a very similar problem. And as before, we have two unknowns, our two final velocities, and we have two equations. But now there's an extra term in our equation. The temptation to avoid is to say, I have two equations and two unknowns, let me just go, right? You could just go through and start doing the algebra here, and you would arrive at absolutely the right answer. Or you could stop for a minute and you think about this. And you say, okay, these two conservation laws hold in any inertial reference frame, any frame that's not accelerating. There's no reason in particular that we just happen to be using this one where, this is sort of the stationary reference frame where the balls are colliding on a table in front of us or something, right? But there's precisely nothing special about that, except that it's the one that matches our view of an experiment that looks like this. But mathematically, that's a bias, right? There's nothing special about that except that it happens to be the one that your eyeballs would have, but who cares? And so you look at this and you say, well, I could choose any reference frame that I want. Are there any that are more convenient than others? And in this case, of course there is. What would be the better choice of reference frame here? Here's all you do. You say, well, we've complicated this a little bit by giving that big mass some initial velocity. Let's just choose a reference frame that moves along with the big mass at the beginning of the collision. Right? So that changes our velocities a little bit. So we're saying we're not going to solve this problem using the ball velocities as measured in this reference frame where we're watching them on the table. We're going to solve this problem instead in a also inertial reference frame that just happens to be moving along with the big mass before the collision. So in other words, we're coming up with new velocities, which I'm just indicating with the little tilde. But all we're saying is the initial velocity of that incident mass, the littler one as written up there, is just going to be the original one in our sort of experimental reference frame minus the initial velocity of the big one. In other words, we're just taking all of our initial velocities and subtracting off the big one. Those two conservation laws are just as true in this reference frame as the other one. But when we do this, it reduces to exactly the problem that we just solved. And so we already solved this. We don't have to do any algebra. We just plug in the answer here. We know exactly what the solution to this is. It's the following, because we just solved for it. But then, as I said, so at this point, the problem's solved. Now, like I said, perhaps we care about representing the solution in the reference frame of the experimenter watching these things collide, and that's fine. Then as a last step, we know how to translate from the tilde frame back to the non-tilde frame. So we just translate the solution back, right? We just say, we'll just plug in everywhere that a VF tilde appears. We know that VF tilde is just V final minus V initial in this other reference frame. Just plug it into the solution. And what we end up with is the final velocities of those two balls, now back in the reference frame of the experimental observer. But we didn't solve the problem in this frame. We solved it in the more convenient frame and then just pop back at the end. It's way easier. Saves us a bunch of work, error-prone work. So let's add one more layer of complexity. Actually, we're going to add two more. Now let's suppose our balls aren't moving on a line. They're moving in a plane. And so our incident mass comes in and it strikes this stationary mass big M and then, they both sort of move off. And our question is exactly the same. Given that we know the initial velocity of the balls and the initial masses of the balls, what are their final velocities? We're asking the same exact question. And so we could absolutely write down the same two conservation equations that we did previously. We know that momentum is conserved through this collision, and we know that energy is conserved through this collision. This is fully elastic collision, so we're assuming everything's conserved. But now that we're in a plane, all that's changed is these are vector equations instead of scalar equations. But that's okay. It's telling us exactly the same thing. So we could, if we wanted to, say, this is x, this is y, here's my equations, and just start chugging through the math. And you would arrive at the right answers. But the physicist might stop and think about this a little bit and say, well, I can choose any reference frame I want. I can also choose any orthogonal coordinate system that I want. Are there any that make my life easier? Right? And so the thing to recall here is that the conserved quantity in the case of, say, momentum is a vector. Momentum is a vector in this case. The fact that that vector is conserved, the thing that's conserved is the vector. We can talk about that vector in any set of orthogonal bases that we want. We could say this is x, y, or we could tilt it this way, and that's perfectly fine, right? We're talking about the same vector. We're just talking about different representations of it. And then broken into its components in any orthogonal basis, because the vector is conserved, the components of that vector are conserved, right? So we can take this vector equation and break it into two scalar equations if we want to, that describe the two components of this vector in whatever basis that we've chosen. You can imagine that this is maybe x, y, or something, right? And we could talk about the preservation of that vector in that coordinate system. But we needn't say that y is straight up and x is straight over and choose anything that we want. Is there a particular basis that makes our life easier here? Does anybody have a clue, have a thought with regard to, what I'm describing is we want an xy coordinate system, but we are free to rotate it however we want, right? Doesn't matter. Physics doesn't care. Is there a particular orientation of xy that makes our life easy here? That's a thought. That's a thought. Not exactly. One thing that we could remember, when these two balls collide, there's a force exerted between them. That force is a normal force, right? A normal force between two surfaces. The normal force must be orthogonal to the surfaces of both balls. By definition of a normal force, right? It comes straight out the surface. Well, if the force between these two things is normal to the surface of each of them, that means the force must act strictly along the line that connects the centers of the two balls. Does that make sense? We can't have forces acting in any direction because these are normal forces except directly along the line that connects the two centers. And so one strategic choice of bases that we could choose is one where one of our basis vectors points directly along the line where the force acts, and the other one is orthogonal to it. The conservation equations are just as true if we represent our vectors in this coordinate system as any other coordinate system. But in this coordinate system, the force only acts in one direction and directly along the vector. So if we do that, this is just summarizing the points that I just sort of waved my hands at. Let me just make sure I hit all of them. So like I said, it's the normal force that affects their motion, collision between two surfaces. That force is perpendicular to these two surfaces, so it must act along the line that connects the centers of the ball. And then remember that by definition, all that force is change in momentum with respect to time. That is the definition of force. And so that means the only change in momentum is in the direction of this force, the line that connects the centers of the two balls. And so instead of saying y, x, and just plugging through, we stop and think for a minute and say, okay, let's change our orientation just here a little bit. And as a consequence, things simplify considerably. So I'm calling these, we could call these directions anything that we wanted. I'm calling this the perpendicular axis and the parallel axis, which is just to say this is parallel. Well, maybe this should be swapped. In any case, you get my point. V perpendicular is in the direction of the line connecting the two centers. V parallel is orthogonal. So we can write down our conservation laws in these two reference frames, and that's perfectly fine, right? This is describing the conservation of the momentum vector. We're just breaking it into components in our two axes. But in these axes, the force only acts in the perpendicular direction, right? And so what that implies is that that implies the only change in momentum is in that direction. Momentum is mass times velocity, right? The masses aren't changing, so the only change in velocity is in that direction. So that means that in these coordinate systems, the initial velocity of the little mass in the parallel direction must be the same as the final velocity in the parallel direction. So we know there's no change in momentum in this direction. And furthermore, the initial velocity of the big mass, which we said was 0, must be the same. Can't change. There's no force acting in this direction. So there's no change in momentum in that direction. So there's no change in velocity in that direction. Everything is occurring in the other direction, which gives us, it reduces us back to this scalar equation. That's the equation that we just solved. That's exactly the same. We're back. We've reduced this back to exactly the same situation as the simplest conceivable version of this problem. In the direction in which the force acts, this is a 1D problem. And by rotating our axis such that that force is perfectly along one of our axes, we've reduced the 2D problem back down to the 1D problem that we solved. And so we don't need to solve this. We already have solved it. We know that in this parallel direction, the component of the velocity in this, this perpendicular direction, we've already got the expressions for it as functions of the initial velocities in that perpendicular direction. And so at this point, the problem is solved. Perhaps it's not in the frame of reference that we ultimately want to represent the solution in, right? Maybe we're in some camera view looking down where x is this way and y is this way or whatever. And so maybe we want to bring it back. But the problem's solved at this point. All we have to do is translate back to whatever coordinate system we care to. And that's not so hard. So how do you find the initial velocity, that term there? How do we solve for the initial velocity of the little incident mass in that perpendicular direction? The way that we do this is we take its initial velocity and we do the dot product between that initial velocity and the unit vector that points from the big mass to the little mass, right? So that is to say, we find the unit vector that points from the center of this circle to the center of this circle, and if we do the dot product of that unit vector with our initial mass, what we end up with is the initial velocity of that little mass in that direction, in that perpendicular direction. So this is us solving for the vector that points from the center of the big mass to the center of the little mass. And then if we want to make that a unit vector, we just divide by its magnitude. Divide by its magnitude. Now that's a unit vector, a unit length vector that points from the center of the big mass to the center of the little mass. If we dot that with the initial velocity of our ball in our, xy table coordinates, what we end up with is the component of that velocity that's in the direction of the force. So we're just translating our solution back. And so we can substitute that back into our expression here. So we solved for v initial in the perpendicular direction from our original table coordinates, and substituting back in, we end up with this final expression. And likewise for the other one. And I wanted to mention too, because this connects to your pseudocode, it can be convenient for making, say, animations of this, instead of solving for the final velocity after the collision, sometimes it's handy to solve for the change in velocity as a consequence of the collision, which is easily enough done. The change in velocity is the final after the collision minus the initial before the collision. Substitute in the final and initial velocities here, right, and do some algebra, and you end up with an expression that is the change in velocity, a vector expression for the change in velocity as a function of that collision. And by exactly similar analysis, we can do the same for the bigger mass as well, and the change in velocity of the bigger mass. Okay, so the last generalization here that I'll just bring up is, and perhaps we won't go through this in the same excruciating detail as the previous ones, is now let's suppose we have a glancing collision in the plane between two balls of non-equal masses where both are moving. And solving this problem involves a combination of the two techniques that we saw already. Remember, one of our first techniques was let's choose a reference frame that moves along with the big mass. And then furthermore, let's choose a coordinate system that is oriented such that one of the axes aligns with the direction of the force. So you combine those two techniques that, again, we've already seen. And what it allows for you to do is solve this problem without actually really doing any algebra. Right? So all that we've done is we can write down our conservation equations. We choose to change reference frames such that we're moving along with the big mass. Okay, so here's our new set of conservation equations. And then this is a system that we already solved. This now reduced to exactly the previous version of this in which the big mass was stationary. So we solve this in the tilde reference frame. And then, as we saw previously, it's a simple matter to go back to the reference frame that we care about. We just add back on the initial velocity of that big mass. And we end up with the solutions in the sort of table frame. And again, we can solve for the changes in velocity if we care to. So, but in the lab, you are not doing collisions between balls. You're doing a collision between a ball and a peg. Now the advantage, and this is another sort of physicist thing, the advantage of solving for the most general form of an equation is that then if you're interested in a specific version of it, you take that most general form and send some things to infinity, send some things to 0, and it reduces back to the special case form that you're interested in. Let me show you an example of that. So for instance, let's suppose a situation where our little ball is not bouncing off of another ball that then moves, but instead bouncing off of a wall, which we should have a good physical intuition for, right? Which is nice. So the most general form of the equation that, again, we just solved for, and this is written as a change in velocity, is given here. We want to take this most general form of the equation and modify it such that it describes this situation. So what is a wall? A wall is a ball with infinite radius. Right? Take that ball and you just make it bigger, 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 and when the radius gets infinity, you've got a wall, a perfectly flat wall. So the radius of the wall is an infinite radius ball, which raises this question. We are interested in this term here. I'll just remind you, describes the unit vector that points from the center of the big ball to the center of the middle ball. If your big ball assumes a infinite radius, this reduces to what? Just the normal vector. So this term here, again, which for balls describes the line that connects the two centers, if the radius of one of them is infinite, that's just the normal vector, right? Anywhere that this collides, the center of this ball is infinity that way, right? And so the line just goes straight into the wall. So it's of infinite radius, and because it doesn't move, one way to mathematically state this thing doesn't move is to say its mass is infinite. And so let's see what happens to this equation as we make those adjustments. So, like I said, the unit vector that points from the center of big M to the center of little m reduces to the normal vector, because the center of big M is infinity that way. So that leads to a simpler looking equation. And furthermore, oh, another thing, the wall isn't moving, of course, and so big VI here, the initial velocity of the big ball, is 0 because the wall is stationary. So that term simplifies there. We're not left with little v minus big V, but just little v. And furthermore, the mass of our wall is infinite. And so this term here, we take the limit as big M approaches infinity, which is, of course, just 2, right? And so you end up with the following simplified version of that most general equation for the situation where you don't have two balls glancing off one another. One of the balls is a wall. And you can do a quick sanity check here, where you say, okay, let's imagine that I have a ball coming in towards the wall with an x velocity, coming in at the wall. What's the velocity that I leave with? This is just illustrating that, as should probably match your intuition, it just reverses. It bounces off, boing, right? Okay. We can take some other interesting limits. Here, this is what I've been trying to build to. So we're not bouncing off a wall. You guys are bouncing off of a round peg. What is a round peg but a ball with infinite mass, right? A round peg is just another ball that we're bouncing off of, but it doesn't move. One way to mathematically state it doesn't move is to say its mass is effectively infinite. And so we can take our most general form of the equation that we solve for relatively easily by just thinking for a moment about what reference frame should I be in? What coordinate system should I be using? We solve the simplest version and then basically use that to solve the most general version. And now we're taking that most general version and reducing it back to the situation that we care about, which is this one. So here's our most general form of the equation, right? And then we say, let's let m go to infinity. When m go to infinity, just like we saw previously, this term here becomes 2. That's the limit of that fraction as big M goes to infinity. So we end up with the following. Minus 2 times the dot product between the unit vector that points from the big mass to the little mass, from the peg to the ball, that unit vector from peg to ball, center to center, times the dotted with the difference in initial velocities of the peg and ball. In what direction? In the direction from the center of the big ball, the peg, to the center of the ball. Center of the peg to the center of the ball. It simplifies even a little bit further, though, because, of course, the peg is stationary. So VI is 0. So what this reduces to is unit vector from center of peg to center of ball, dotted with the initial velocity of the ball. So what this is asking is, please tell me the component of the ball's initial velocity that is in the direction pointed straight towards the center of the peg, because that's the direction that the force is acting. Minus 2, right? And then in what direction? In the direction from the center of the peg to the center of the ball. This is a unit vector. So this describes our change in velocity after colliding with the peg. The change in velocity is in the direction from the center of the peg to the center of the ball because it's a normal force, so it must be. And of course, this is an obvious point, but if you were to look at the analogous equation for the change in velocity of the peg, as you let m go to infinity, that of course goes to 0, right? Because the peg doesn't change velocity as the mass goes to infinity. So this equation here is this line. So that slightly obscure line comes from these collision physics. we're essentially out of time. So I will just remind you that in the event some of this stuff's a little bit rusty, and you would like to actually see every algebraic step that I sort of waved my hands at here, the write-up on this includes every algebraic step building up, as we go to increasingly complicated situations. This one then goes a little bit further than we went here in class and includes a coefficient of restitution, which is to say some term that describes the loss of energy during a collision. As I mentioned, to be physically correct, that loss of energy is in the direction between the center of the peg and the ball. For us, because we're not modeling the loss of energy due to rotations and spin and so forth, in order to get a Galton board that looks the most right, we're stripping energy off from all directions. So to summarize this, what I'm trying to advocate for, I suppose, is try to avoid the temptation to solve a problem in the coordinate system that you ultimately want the solution represented in. It's a temptation I still have to avoid as well. Instead, look at the problem and ask yourself, what is the natural set of coordinates in which to solve this? Solve the problem in the natural set of coordinates, and then once you have the solution, say, okay, now how do I get from this coordinate system to that one that I care about? And you translate the solution at the end as a final step, instead of going through all of the math in this slightly cumbersome coordinate system. And likewise for reference frames. There is nothing sacred about one inertial reference frame as compared to another inertial reference frame as far as these problems are concerned. And so beware of the unconscious bias of solving the problem in the reference frame that you imagine yourself being in as the observer. Mathematically, that's a bias, which is sometimes inappropriate. It's just easy to place yourself sort of next to the table watching these balls collide. But relax that a little bit and allow for yourself to ask, is it easier for me to think about this problem if I'm riding on the ball? It often is, or some analogous kind of change in reference frame. And then once you've got it solved, just like the coordinate systems, then as a last step, translate it back to your experimental reference frame, the one in which your sensors are actually observing this thing. Or if you have a camera set up watching the balls, the one in which the camera actually sees the balls colliding. But you needn't solve the problem in that reference frame. You just have to ultimately represent the solution in that frame. Okay, so I will be in lab this afternoon. And I think in the coming lectures, the gap that I would like to fill in with regard to lab 2 here is the VGA stuff. And so in the coming lectures, I think we're going to start talking about PIO, those PIO coprocessors. We'll start with simple applications of PIO, but we'll start with those simple things so that we can build our way up to an explanation of that VGA driver. This, I'll remind you, that discussion will be one layer of abstraction probably below where most of your engineering will take place. Like I said, anytime something is abstracted from you, I want you to know what's being abstracted. And furthermore, you'll need to know a little bit about how this works if you want to overclock your system, because you have to modify the PIO programs just a little bit. And so the next few lectures, I'm going to be building up to an explanation of how you modify the VGA driver in order to overclock it. In order to understand that modification, we have to talk a little bit about PIO, and we have to talk about the VGA standard and so on. So that's going to be the goal of the next few lectures, I think. Okay, I will see some of you this afternoon, and I'll see the rest of you on Friday.